So here's an example with the quick and dirty method. You see that it's indeed very quick and indeed quite dirty, and nevertheless it actually works. So take some here the space is of course f2, and then we define an take the canonical basis and define the operator T by its matrix with respect to the canonical basis being this matrix. And now let's find a Jordan basis for this operator. Well, we compute the characteristic polynomial, the sense of the usual sense of characteristic polynomial. That's really the determinant of the matrix minus lambda times the identity, where lambda remains as a free variable. This gives a polynomial. We find the roots of that polynomial. I'm not doing that whole process here. You get that only lambda equal 2 is an eigenvalue. Okay, so let's do the quick and dirty method. How was it? You pick a random vector. I picked this one. It's pretty random, 5 and 3. And now what we do with this, we'll take u prime to be n minus lambda a times the vector minus lambda times the vector. So you multiply, you compute this, and you get this other vector. Finished. You found two vectors. So you have successfully found two vectors. They are linearly independent, so the quick and dirty method succeeded. You know already. Well, suppose you're not quite so confident, then you can check. You can write the first vector here. We have to write them backwards. Write the first vector here, write the second vector here, and compute what is A, what is the vector, the operator T with respect to this basis, which basis u prime u, this basis, and you get this. That's a Jordan form. Eigenvalue here, 1 here. Let's go to another example. Okay, here, larger example, a 3 by 3 matrix. So let's try with the quick and dirty method. So we compute the characteristic polynomial, we find its roots, and we see that there are two eigenvalues, 1 and 0. For the eigenvalue equals 0, we look for the eigenvalues, eigenvectors. We just found one eigenvector, and now we solve this equation. So since lambda equals 0, there is a term missing here because the term will be 0. And you see there's no solutions. Okay? Why there's no solutions? You write a linear system, a 3 by 3 linear system, the augmented matrix where u is on the right, and the echelon form will have a pivot in the last column, and this means there is no solutions to this system. So okay, we are done with lambda equals 0. So lambda equals 0 is done. Hopefully one vector will be enough for lambda equals 0. Now we move to lambda equal 1. So we first solve a x equal x. What is this? We're actually finding eigenvalues, eigenvectors, and we get an eigenvector. And now we take the solution of this equation. X here is the variable in the equation, but the solution we called it v, and then we put this v here. And remember, when we write this 1 minus 1, 5 is just a short notation for 1 minus 1, 5. Okay? So this is to be understood as a column vector. So now we solve the system. Okay? Here is x is again the variable in the system, and here there is the eigenvalue here, 1 in front of v that we can see. Then we find the solution. And then we do one more time, we see it has no solutions. And again, because the echelon form of the system will have a pivot in the last column. And now we stop and we just look, we got 3 vectors. We got 3 vectors for a problem, a 3 by 3 matrix. So it looks like we succeeded. Are these vectors linearly independent? Well, they are actually. Why? This vector here, v, this vector v, and v prime, they must be linearly independent. Why? Because if we apply n to v prime, we get v, and if we apply n to v, we get 0. what is n? Of course, n here, n equals t minus the eigenvalue, which is 1, times the identity. And these must be linearly independent. What about the third vector? What about this vector u that we found here? Well, the entire collection has to be linearly independent because these two, they belong to one generalized eigenspace. And this one belongs to another generalized eigenspace. And these two, they were already linearly independent to start with. Yeah, so we know the method succeeded. We can tell already that it succeeded, but since this was so quick and so dirty, we want to check, don't we? So we take u, we put it here, then we take v, put it here, and v prime, put it here. And then we see that the operator t, written with respect to this basis that we found, will be this. Here's our Jordan form, eigenvalue, 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 1. So, and here, this is one Jordan block, this is one Jordan block.